Okay, so welcome to the second session of Wednesday, and Aarne is going to talk about GFUD.
Thanks, Inari, and good morning, everyone, or whatever time it is. This has become a standing joke. Let's share my screen, and can you see this?
Yes, we can.
Full screen presentation now.
Yeah.
Good. So this is about grammatical framework and universal dependencies. And it's actually an example of something that I've been up to with some others for the recent years in our research. So I don't think we have seen so much of that in the summer schools. So it's Krasimir and Normunds and Prasant, and we published together this paper in Computational Linguistics journal last year about scaling up the grammatical framework from controlled languages to robust pipelines. And it has very much to do with the relations of GF with other formalisms that have something interlingual in them. And one of them was WordNet, and the other one was FrameNet. And then there was universal dependencies. And I'm going to talk about universal dependencies now. Another aspect of this interest in the last few years is that I've been teaching this course entitled Computational Syntax at the University of Gothenburg for the Masters of Language Technology program. And when I started it some 10 years ago, so then it was almost only GF, but now since a couple of years back, so it has been about half UD and half GF. So both because it's nice to kind of learn and teach something new, and also because one could say that UD is nowadays the mainstream in computational linguistics, and it's good for the students to know about it. But then also because I think there is a lot in common between these two approaches, as I hope we will see. So this link goes to the course notes, which is in some sense becoming a GF book, which relates it to, for instance, UD and some other more general themes. And the one way to see this interest is that everyone knows that actual language, which is here shown with a dashed contour, is actual natural language is something which doesn't have firm or well-defined boundaries, but it's a kind of not defined mathematically what is exactly correct English or some other natural language. Whereas if you are doing something computational, then you are of course having a mathematical definition or algorithm which at least implicitly defines what the language is. And I think one can approach this from two directions. So one can approach it from below and from above. And when we are doing generative grammar or generation in the NLG sense, so then we want to have something which is certainly in the actual language, certainly grammatical, but it can be smaller. But when we are parsing language, then we want to make sure that we can parse everything that there is in the language. And therefore the analysis grammar or the parser algorithm is actually has to be larger than what the actual language is. And this is where I think UD is doing a very good job. So UD is universal dependencies, and I think I will just show one thing which is to start with, which is relevant here, is that it's an open source community project which has great many languages. So there are more than 100, and there are new ones coming all the time. So there are some upcoming languages, and there are actually some resource grammar languages that are in neither group, but there is, for instance, the core language here in upcoming languages is getting built by David Bamotura in kind of basically GF-based project. So I will talk about those relations a bit later today, or I mean in this talk. But let's go back to the presentation for a while. So I hope you are not seeing my toolbar, are you? Can never be sure, because for me it's quite disturbing.
I don't see it.
Sorry?
Yeah,
you can't see
it. No, we don't see it.
That's good, yeah. So you never know what people can see in Zoom, at least. So this is something that we have always used as a standing example for UD parsing, because it shows many of the central relations. So the usual format in which parse trees are shown is kind of vertical, where you have the tokens, and then in this first column, and then you lemmatize them. So you see nothing very much happens here, but you see that C's become C and us becomes we. Then you part of speech tag them, and of course in practice you do these two things simultaneously, and also the morphological analysis. So this is often the input to UD parsing. So you already have a morphological analyzer and part of speech tagger, but that can also be done in one kind of end-to-end process in UD parsers. So you can actually choose. So the syntactic parsing itself comes at the next steps, and this is maybe something new to some of you. So you get now you have to number the words, tokens, and then you have to create links. And while you are creating the links between the tokens, you also create relations between the words. So it all starts with the root verb, which is usually a verb, but not necessarily. And then you find its subject, which is related to the verb. You find its object, and you find an adverbial modifier. And then for the subject, you find a determiner and an adjectival modifier. Okay, so I'm not terribly used to reading this notation. So usually it's nicer to see it in this way, where you have a tree built by arcs over the words, and then links going from what is called the head to its dependents. So the verb sees is here the head of the subject cat and the object us, and then the subject itself is the head of the determiner and the adjectival modifier. So one thing which is the ambition of UD is that the same tags, these dependency labels, are used for all languages. I mean, all of these over 100 languages. So they have more or less the same labels. Then they can have some of their own, and then there are some conventions which can be a bit different of how the labels are used. But in principle, the labels are the same for all of the languages. So here we have Bulgarian and Portuguese. There's also something that is called Manning's law, comes from Chris Manning in Stanford, which is the ambitions of of UD. And actually in this computational linguistics paper, we also discuss if GF obeys to this Manning's law from point to point. So you can read about that here. But interesting things is here that you have this good for linguistic typology, rapid consistent annotation, then computer parsing with high accuracy, so one can, that maybe is suitable for that, but I don't think it's maybe not quite as accurate as you would expect, for instance, for the purpose of generating language from the result. Should be easily comprehended, used by a non-linguist, that I don't know. And then provide good support for downstream NLP tasks. And that's, of course, certainly a common ambition with GF. There is something more about the UD labels, and I think we will see some trees later. So yeah, so I was actually planning to show some from these slides. So there are about 50 different labels, and here is an example of each of them. And then the interesting thing is also to consider the distribution of labels in different languages. So here we have in English and Finnish standard tree banks. Actually, they are comparable tree banks because there's a parallel tree bank where all the sentences are translations of each other. And you see already from here some interesting facts between Finnish and English, for instance. And in English case is the most important one because it covers the prepositions, whereas in Finnish it comes somewhere far down. Determiner, the same thing, very common in English, but much less common in Finnish, which doesn't have articles. But then when you go to en subj, so then it's in the same, somewhere in the similar place. And oblique and object are, well, we will see what they are, but actually here this depends probably in a bit different interpretation in what is a direct object and what is oblique in English versus Finnish. So when these tree banks are built, so humans do in such a way that at least we learn to do it at the course, that you first mark the root of the tree, you find that, and then you mark its dependence and then its dependence recursively until all words have been marked with exactly one head and label. And one of the learning outcomes of the computational syntax course was that the students were able to annotate any sentence in their own chosen language, which was something different from English. So I will just show some examples. So here you have the difference between object and oblique. So if you have wine and it is object and to beer is oblique. So oblique in English is basically any prepositional phrase that is an argument or an adjunct of the verb. Here is something more complex. So you have also adverbial clause modifiers, and then you have marks for subjunctions and so on. So I think I will not go much further with that right now, but we will see some more examples later. And you can read about, so I think I didn't find any such systematic presentation of the labels, where you can find it on the UD web page, but then I have in this course notes, so we have some yeah, maybe from a more interlingual perspective, the presentation of all these concepts. So let's go further. So there is this GFUD software that the title of this talk is about. So it's a kind of a side project which I've been working on very much in connection to that course, but also to do some other experiments. So it started by ways of converting between UD and GF, but then it turned out that that there was a lot of interesting things we could just do in terms of analyzing and converting dependency trees. So I will show a demo a bit later how this works and what the different functionalities are. They also documented in the README and some other documents under the GFUD. So now to the relations of GF and UD. So it's actually something that you already saw in minibar if you have used that and clicked at the language-specific syntax tree icons with a resource demo. So then you will see the dependency trees. In GF shell, you have the command visualize dependencies or VD. And then in the GFUD, you have another version of that, which is not yet and I don't know if it will ever be integrated with GF itself, which is already quite heavy. But it is a bit kind of further development of what is in the GF shell. So I think I will not show the more examples now, but I go to the algorithms, and then I will go to the other applications like visualization of. So in the minibar, the essential use of the dependency trees is as visualization of the GF parses, but then other applications are tree bank synthesis and tree bank augmentation, which I will talk a bit about. And the basic idea is that instead of manually writing tree banks, like manually parsing sentences, you can generate a tree bank from the GF trees and then try and train the parser with that to save some work. So I will come back to that. Or you can augment a given tree bank with more trees. And then there are also some other applications that we will see. Also, Arianna's talk after this is an application. So now this relates to some version of the old mini resource where you have, which is by now quite familiar to all of you, I hope, or at least I assume. And I have here the syntax tree for the black cat sees us today, according to this abstract syntax. And when you are running GF to UD, then you start by adding a dependency configuration to each of the abstract syntax functions. So for each argument, you attach a dependency label, and one of those labels must be the head. So if you have just one argument, so then it's always the head, and it doesn't really matter. You don't need to write it manually. But otherwise, there's a configuration where you have these, and you see that in PredVP, so the first noun phrase is the subject, and then the second, the verb phrase is the head, or actually because the subjects and the heads are always words and not phrases. So this means that the subject is found in the noun phrase and the head is found in the verb phrase. Then for complementation, there is head in the verb is the head, and then there is a d-obj. So this is actually an old terminology in UD version 1, where obj was called d-obj. So these slides are a bit old and reflect that difference. So when you have this abstract syntax tree, then you start by annotating all of the branches in the tree, or all of the subtrees here with these labels according to this. And then you have a labeled tree, and you can throw away the configurations, because now you can work from here. So when you start from left to right, finding the head and of each word, so that you go up the tree until you hit a label, and then you go down the head path. So the head labels are not marked here. So you go down to the head path, and then you find it's the head of this dependent. So you see that the is a determiner of the head cat. The same thing with black. Then cat is the subject of C. And then when you go up from C, then you don't find any label, so it goes all the way up out of the tree, the so-called root, and then we and today. Okay, so this is now the dependency tree, and now you can throw away the GF structure, and what is left is the dependency tree, which you can then display in this nicer notation. Well, this is exactly the same, except that, well, you have also done lexical insertion here, and then you also need a little mapping from the syntactic categories to the universal post tags of UD. So here you see that you can't really see it here, but for instance, for verbs, there is just one post tag for all valencies of the verb. So the valency of the verb is something that UD doesn't try to resolve in any way, but it treats all of the, for instance, all of the arguments and adjuncts in the same way. So that's one loss of information when you compare with the GF. But anyway, so use this mapping to put the part of speech tags here. And then you can also do the same as a kind of modified version of linearization. You can, for all languages in the RGL, so you can derive these universal dependency trees. So if you think about the different kinds of trees that there are, for instance, in the minibar and GF in general, so you have the abstract syntax tree, which in GF is the core of everything, which is language independent and which is built from functions. So it's lossless because you can determine both the categories and dependencies from that. Whereas the parse tree is language dependent, so it's built from categories and words, and it's glossy because it does not determine the dependencies, let alone the functions of GF in the GF sense. And then the dependency tree is also language dependent because it has the words on the on its leaves, but well, language independent in the sense that it uses similar labels. So it's also lossy because it doesn't determine the categories, for instance, the different verb categories, and of course it doesn't quite determine the functions. But there is a good, at least, hope that when you have a dependency tree and this dependency configuration, you can search for the set of possible GF trees that linearize to that dependency tree. So anyway, so from abstract syntax trees, you can generate both kinds of trees, and these are what you can see in the minibar illustrations or visualizations. And there is a lot of earlier literature where with attempts to translate between these two kinds of trees. For instance, the Penn tree bank was converted to a dependency tree bank from parse tree bank long ago. But this is a kind of heuristic procedure, and then what the GF can add to this is that you can actually do this in a more deterministic way because the abstract syntax trees are lossless. Anyway, so there is one difference and one problem, and that's actually so far GF to UD has been very simple, but then you have these syncategorematic words, which are words that do not have their own category in GF, and they never occur as arguments in a GF tree, but they are added in the linearization. And this pinpoints a difference in the ways of thinking. So dependency grammar is about words and GF is about meanings, or maybe one could say about trees. So here is an example of categorimatic word, like cat is a noun, so it has its own category and function. Here is an example of a syncategorimatic word, a word that is between categories. So like the copula is in adjectival predication. So there is no label attached to this in the abstract configuration, because this tree only has the head, which is the adjective, and is left without a label when you do the way I showed in this small animation. So the result would be a tree like this, and this is not what you want to have in UD, and it's actually not even valid. So because there is one word which is without a head. There is a baseline way to fix this, which is that you add a default label, which is conventionally called dep, and then you see that this comes from the verb phrase where it was built. So that's the part of speech tag, but none of this is desirable. So what you actually want to have is that it is a copula, and actually in the current version of UD, so this would be an auxiliary, augs and not a verb. But anyway, so this is what you want in UD. And how to get to this? So you could rewrite the grammar so that you actually have a copula in there, and there is just one copula B, and then you follow the same algorithm as earlier, but this is not the approach that we have usually followed, because the other approach is to extend the dependency configurations. So we basically have both abstract and concrete configurations, and moreover both local, as we had before, and non-local. And again, I will not go to the details of all of this. I will show some examples, but the main thing is here that it's well, you do these configurations and it's more complicated and it's not universal, so you have to do them for all languages separately. But it's probably less work than rewriting the grammar, and it's certainly more flexible because UD can change, and it actually has already changed. So we want to have the RGL as it is, at least make it possible to have it in that way. And also we can keep the abstract syntax more abstract. For instance, this copula might not be a relevant category in some languages at all, which don't use copulas. So other syncategorimatic words, so in English and other languages, so you have negation words, tense auxiliaries like have and will, infinitive marks, to, and sometimes prepositions are also syncategorimatic. And these are actually interesting also because when you do some collapsing of the dependency trees, which is one way to approach, for instance, semantic role labeling. So then you don't care about these auxiliary words. So then these are typically the ones that come out as syncategorimatic in GF. Well, of course, you shouldn't forget the negation, so you have to, and also the tenses. So, but maybe infinitive marks are certainly not very important. So one way you can then use this generation is that you have a tree bank, and you can have a simple program for adding trees to it. So let's say you have a tree for a present tense sentence. The black cat sees us. Then you run UD to GF, and I will come back to what that is. And then you augment that to some other GF trees, like which vary the tense and the polarity, and then you can generate new and typically much more complex trees in the UD format, which can be useful for getting a bigger tree bank for free and training with that again. The other, and so actually I must say that we haven't tested with this very much. What we have done more experiments with is cross-lingual bootstrapping. So in this paper from 2016 with Prashant, so we did it to the then 36 languages in the RGL. And the abstract rules, I mean the configurations which were common to all languages were usually enough for 80% of the edges. So here is an kind of more statistics about that from that early date. And here are some examples. So one of the interesting features in UD is how they treat conjunction, because that's not really a dependency relation, but it's a kind of more symmetric relation. But they still, the way it is done is that when you have a conjunction, then the first conjunct is the head, and the second conjunct is the dependent with the label conj, and the conjunction word is CC, or conjunctive conjunction. And I think at least these in the current UD, it's not connected to the first conjunction, but it is connected to the second conjunct. So this is not quite as UD would expect it. So to get it right again, we need some non-local configuration. And here are some more languages which show this example. Prashant also did an experiment with converting the GF pen tree bank that Krasimir had created long ago, and with interesting features. So it was about this the match with the standard dependency tree bank created from the pen tree bank was about almost 80%. But there was some more work to be done with these modal verbs and also with compounds, which is another bit tricky chapter in UD, and especially when you, so in GF you often create these multi-word expressions as like atomic expressions, but from UD they have to be split into their different tokens. This was another synthetic tree bank experiment by Prashant and me, which was published 2 years ago. So we generated random trees, I mean completely from scratch, and then we trained parsers with different numbers of trees and saw how good the parsing accuracy was with respect to a test tree bank, which was not generated by us, but which was the standard native tree bank. And in both languages, we ended up somewhere around the 60s. We have done this for some other languages as well, but this is an interesting pair to compare. And what you can see here is that in English, so actually you get very quite soon to the level which is as good as these. So what happens with this synthesized tree bank, the red one, is that it kind of, there is a point from which it doesn't really improve, whereas the natural tree bank seems to continue improving. But in any case, so you can reach a kind of acceptable level for free, if you consider 60 an acceptable level. So you can reach it by these synthesized tree banks, and then you can kind of bootstrap a parser for a language. In this case, for a language for which you have an RGL, but you don't have a dependency tree bank yet. So this is one, might be an interesting experiment to work more on. And we had this year a master's thesis by Elena Rodriguez Raposo, where we tried to improve these 60s, and it turned out not to be that easy, but we learned quite many things from that process. And yeah, maybe a bit more about that later. Here is a hands-on synthesis experiment, which I think I will also show when it comes to demo time. So you can actually, this is all that you need to do. So you generate a training corpus from random GF trees here, and I did this for Minilang to get this in small limits. Then you convert these GF trees to UD trees, and then you train a parser with UD pipe. This is the phase that takes a long time, several minutes at least, even for this small tree bank. Then you parse input and try this kind of test this in an ocular way. But then you also generate the test corpus, and actually here I should have done it in a slightly different way. So generate the test corpus and the training corpus at the same time, and then just cut parts of them, so to be sure that they are distinct. But yeah, so there are many methods of doing this. Then you parse the test corpus with UD pipe. So UD pipe is the software that is come from Prague, which is a kind of easily usable, out of the box usable neural network parser and parser generator. And you parse the test corpus with UD pipe, and then you evaluate the results. So you compare the labels in these two corpora, the kind of the gold standard and the one that was generated. So I will show the results in a while. First, just show that you can actually do this with any grammar, and this can be an interesting way of building a kind of a robust parser front end to a GF system, where you have here the most obvious experiment is to have arithmetic terms formed from plus, minus, and times, just one atom, which is X, and then you have these two ways of combining, well, two combination rules where you build infix expressions, where you treat the operator as the head and then the arguments as the two dependents. Okay, so I will show that in a while as well, but now let's look at the UD to GF a bit briefly. So the idea is that with UD to GF, you would get from dependency tree to abstract syntax tree, so that you could actually use this as a front end to GF, where you parse the source with the dependency parser, and then you translate the abstract syntax tree with generating with GF. So you get many translations, and you can also get logical forms or other trees, or like for this augmentation and so on. So the first part is done by a tree bank, and then the second part by the grammar. And here you use these dependency configurations of the kind that I showed you, and then some others has to be added as well. I will not go into details now, but you can find all that in the GitHub. And the rationale of this is that parsing robustness in the dependency parsing, that's robust and fast, and also has context-sensitive disambiguation, like as a built-in feature, whereas GF doesn't have these, at least at the moment. So you can't claim that GF parsing always has these virtues. But on the other hand, GF semantics is compositional, and you can do accurate generation. Then, well, it's questionable whether you can do any kind of generation from dependency trees. They don't have enough information for that. And adding languages, writing grammars is high-level work, and adding languages in dependency grammar is low-level work in the sense that it's kind of annotating individual sentences, although that can be quite some fun as well. And some people might argue that low-level work is a better thing because it's cheaper than the high-level work. But if you do it for fun, and you have more fun from high-level work, so yeah, then this is different. So so the topic here was how you do UD to GF, and I will just show a kind of algorithm that we have tried to implement. This has kind of tries to reverse the GF to UD algorithm as a search problem. But you have these problems that you can have ambiguity on different levels, and then you can have words or nodes in the dependency tree that are not covered in the GF tree. So what do you do then? So then we have extended the grammars with these backup nodes, which are kind of adverbial modifiers that you add to the tree anywhere where you can't really attach it properly. So here is an example of how it works. So you have this English, I have a change in plans next week. And next week is a special thing, nmod, tmod, temporal modifier, where you just use a noun phrase as an adverbial. And that's something that the RGL did not cover when we were doing this. So you treat this as a backup. And when you generate the tree into Swedish, so you get something which is kind of actually good Swedish. So you can also say nästa vecka for next week in Swedish. But if you generate this into Finnish, so obviously it goes down. So you should actually inflect this within the adhesive case. So if you just add to the noun phrase here, so then it doesn't get quite right, but you can at least mark the part of the translation which is not as certain as the other parts. So that's the part where you have used the backup. So I will come back to the conclusions maybe, or yeah, why not say them now. So GF and UD share the ambition of interlingual syntax. GF's strength is in accurate generation, and UD's strength is in robust parsing. And GF-UD works well, but needs that you work on the annotations so that you get the synccategorimatic words right, and also that you get the morphological labels if you want to get them in the format that UD wants them. Tree bank synthesis is promising, but does not yet reach the quality of natural tree banks. But maybe for under-resourced languages where you already have an GF grammar, so it's the way to get started. UD to GF does not scale well yet, so actually it's almost unusable except for the way it is now, because it's very slow. So that's the main problem. And GF-UD has useful GF independent functionalities for UD trees, and I think I will go to those now. So if you have any questions at this point, please let me know. Otherwise, I will show some demos. So I went to this GitHub page where you can find the code, and then I have some tree banks here, and I have prepared some demos which are also listed here. So first of all, so you have GFUD. Higher now. So there are lots and lots of functionalities, as you can see. So we have just added more things when we have needed them. And I will not explain all of those now. But the first thing is that you can check the consistency of the tree bank, and that's kind of okay. But then maybe more interesting is to do statistics. So GFUD statistics deprel, and I have this mini trees kernel, and so GFUD usually reads standard input, so I do it in this way. Oh, so not here, here. And this is the statistics of the from those trees, and then I do this from some standard, let's say NPUD UD test kernel. Okay, and I get different statistics. So that was actually shown on one of the slides. I can also do some other statistics like pos, so which pos tags are the most common, or I can make their combination. So how often is a certain kind of word used with a certain dependency relation? So the most common is punctuation, used as punctuation, and the second one ADP, which is same as add position, like preposition or postposition, used as case, and determiner used and that. So there is kind of very little So then you see nouns are used in and objects and more of you can also compare tree banks. So you can compute the cosine similarity, and which one is now? You have, for instance, deprel, and I have this standard tree banks, and then I have this mini trees. No, I think I have to put it as the last argument. I should have. So you see that they are not very close to each other, which kind of indicates that maybe this is not a very good distribution, and this tree bank is not very good for training if you want to parse the natural corpus. But if you try, for instance, two different natural corpora, so you have NPUD and you have NEWT test kernel. So you see you have two different, entirely different English tree banks have a very high similarity. Whereas then as the last experiment with this, so I will show how you compare with a Finnish tree bank from the same with the same content. And here you see that the languages are kind of a bit different, again, Finnish and English, but let's say also we take, let's say, Swedish, which is another Germanic language. Oh, that didn't exist, so let's see. Okay, well, I have to think. Yeah, never mind. So you can do all of these experiments. You can also check what things are not covered, which is useful when you are trying to train, synthesize a tree bank. Then this is something which is kind of interesting, is pattern matching. So you can try and find different kinds of patterns in the trees. Like, for instance, when an adverbial is used as excomp, so let's try to copy that. And I also take it through more so that you can get. So here you get all of these, and then an even more interesting thing is that you do something a bit more complicated pattern matching. So now I can show you how this. So there's this predicates which looks for certain patterns which basically form the main arguments in a tree. So if you try this, then you find different verb. What you will get as a result is different verb frames, basically. So you see that you kind of summarize this or extract the predication pattern from the full sentence. And this can be a way to, for instance, grow your translation dictionary with verb valencies and other predication patterns. The last thing I wanted to show is the visualization here. So I take just the trees corner and I pipe it to GFUD kernel to PDF. So this is how the three diagrams were created. So they are created in plain LaTeX code, and here with this command, this is you could take them from the LaTeX and then paste into the slides or the paper, or you could also show them directly in the PDF form. And a fun thing that happens when you do this with terms. Yes. So here is what we get for this. Arithmetic terms, so you can get actually dependency trees for those. Okay, so there are many more things that I could show here, but I think we can take questions now, and if there is anything, yeah, any more demos that you would like to see. Michael, did you see some now?
Thanks, Arne. I would actually suggest that we keep this rather short because this is like a lunch and dinner time. I mean, sorry, the time after Arianna's talk is lunch and dinner time, and then we can take more demos after that. So people get to see the 2 talks and then all the demos or whatever after that. But we can take some questions depending on that.
Yeah, let's take some questions. If there are any.
Okay, Karel.
Hello. Maybe I missed it, but do you have some results about data augmentation and this bootstrapping functionality? How much they improve the parse? So these neural networks that you trained on these larger tree banks, how much did these things improve the parsing results?
So we don't have experiments about that, but rather on what happens when you try to synthesize a tree bank. And we got a bit depressively stopped at around 60, 60 points, which is far from the state of the art. Some reviewers commented that this might also be because we are using a rather baseline parser generator, which is a UD pipe, and there are much better ones. But basically, so there seems to be something which is missing from the data that we didn't quite capture. So, but the synthetic tree bank, so you can easily get to around 60 points, and that's the main result that we had.
Okay.
But the augmentation we haven't really tried. Well, yeah, no conclusive results there.
Okay, thank you.
We had a question in chat and then Laurette. So the chat question from Regina: is there any rule of thumb on how the root is derived?
Yeah, so that's the main predicate of the sentence. So it can be the verb if it is a real verb, but if it is the verb is a copula, so then, for instance, I am here, then it's here that is the root, or I am happy, then it's happy that is a root, and I am a teacher, then it's teacher that is a root. So it's the main predicate. So yeah.
Okay, Laurette.
Thanks. Very interesting. We hope we can also work in this direction a bit. I was wondering about the augmentation. I know you didn't do too much of that, but what kinds of augmentation? You showed an example of varying the tense and the polarity and so on. That's on kind of these, on the high aspects of the tree. So when you build a clause, but have you tried any other kinds of augmentation on the trees?
Yeah, so there is some literature on augmentation, which is adding and removing modifiers and adverbials. And actually in a rather primitive way, so they can't, in a way that doesn't guarantee the grammatical correctness because they have no grammar. So we could do that better, and that would be an interesting thing to try out. But,
thank you.
Yeah.
We have another question in the chat.
Cosine similarity, does it support various types of semantic similarity? Well, we can do cosine similarity with all the different combinations of basically the columns in this tree. And also we have a kind of derived thing, which is the subtree. So I will, okay, so I have to show that if I want to show that. So, when you're sharing terminal only. So there is this derived concept of subtree type, where you have a type of subtrees is, let's say, I have to, here, subtree type. Oh yeah, this was the file that did not exist. So I think I have to show you what the subtree type is, and then we can. So subtree type is something that we have also experimented with, actually generating a GF grammar from these, so that a subtree type means that you have a tree where you would have a GF function where the arguments would be a determiner and a noun, and it would create a noun. And then this way it goes. So you have these different combinations of heads and dependents in the tree bank. And you can actually build a statistical model from this, as you can see from here. And then you can get kind of a bit more context dependency in this statistical model than in the, if you have just a model on the individual labels or a model on the individual GF functions. I'm not sure if this answers your question, but it's a kind of a more semantic concept in a sense than the yeah. Enhanced dependencies. Okay. Yeah, well, at least I haven't worked with enhanced dependencies, but if other people have, so that's of course welcome. Okay. Is it time for the next talk now?
Yeah, let's do that. So like if you have more questions, you can always ask them like after Arianna's talks and that conversation. So like, yeah, let's do you want to have like just a tiny break or just
a tiny break? Yeah.
Okay. So
for me, my part.
Yeah. Yes. So like people get to go to the bathroom or get a cup of coffee. So 5 minutes. 5:09. Okay. Let's start the next talk. It's 5:09. So Arianna will talk about concept alignment.
Yes, so I think you see my slides in full screen. Is that so?
Yes, that's correct.
Good. So hi everyone, my name is Arianna, and today I'm going to talk about one more application of GFUD, which is an alignment software that was born sort of as part of my master's thesis, and then I continued developing at Digital Grammars. So let's start with some context. Let's imagine that we are developing a domain-specific machine translation system. And let's imagine that we need very high precision and not necessarily so much coverage. So precision means, on the one hand, grammatical correctness. So we decide to use GF. But then precision also means, and this is equally important, lexical exactness, if we are working in a specific domain, maybe in a technical domain, let's say. And so what we need is a high quality translation lexicon for this machine translation system. A translation lexicon that preserves both semantics and morphological correctness. What is the problem? The problem is that this is a task that we usually have to carry out manually. And first, it is a time-consuming task. Also, it requires significant linguistic knowledge, especially if we're working in a multilingual setting where we have to handle different languages. Maybe we don't know all of them. And I would add that this can easily become quite tedious if done on a large scale. So we want to automate this process of or at least part of this process. And we can do that when we have some example parallel data. What does this data look like? Here is an example of a small parallel corpus. We see two texts, one in English, and then on the right, it's Italian translation. This is exactly the type of input that the software I'm going to describe expects. Because as you can see, this text is sentence aligned. So we have 3 sentences and their translation. And this is, of course, a bilingual case, but this could be in many languages. When it comes to alignment, we can perform alignment at different levels of abstraction. So one case is we want to perform word alignment. So for instance, here we say that nothing in Italian is translated as niente. And another case is when we want to perform phrase alignment. So for instance, here the phrase nothing else to do is translated as niente di meglio da fare. And then there are actually many interesting cases, actually even already in this one sentence. For instance, a more idiomatic sentence is something worth hearing, which becomes qualche cosa di importante. So not a literal translation. This means something that is important. Right. With word alignment and phrase alignment, and of course also sentence alignment, in case the text is not already sentence aligned, is something that has already been studied, obviously. And many statistical machine translation software relies on statistical approaches to word and sentence alignment. When I say statistical approaches, mostly I refer to the IBM models. And these come with some great advantages. So first, they're easy to use. One such example is fast align, which is actually one of the IBM models reparameterized. Then they can handle noisy data, which is quite useful if we work on raw text. And they are fast on large corpora. But of course, statistical approaches also have some disadvantages. So we said that they are fast on large corpora, but it's not like we can use them on very small corpora. And unfortunately, it's usually the case that when we develop a domain-specific translation system, we work with very small sets of sentences. And maybe we even have, for each relevant term or expression, just one occurrence throughout the whole corpus. Then another disadvantage is that when we talk about statistical word alignment, correspondences are between simple strings. So we have no morphological information about the words or phrases that we extract from the corpus. And third disadvantage is that we have to decide a priori what's the level of abstraction we work at. So we can work, for instance, at the word level, at the phrase level, or as we said, at the sentence level. As an alternative, we can analyze the sentences and perform 3-to-3 alignment. So here you see two parse trees. And as our working example, I've chosen a sentence which it looks like it's really a simple example, but that's all deception. So in English, we have the sentence, she missed the boat, intended as an idiomatic expression, meaning she missed the chance, she missed the opportunity. And here is the Italian translation of the sentence, ha perso il treno. And at a first glance, the trees look very similar, but here in Italian, the first thing to notice is that the pronoun she is dropped, as it often happens in Romance languages. And also that the verb missed is expressed with the participle perso and an auxiliary a. So these trees are not identical. And then there's something trickier that we have to notice. So that's here, she missed the chance is expressed like the chance, and she missed the chance is expressed like boat. So we use like this vehicle to represent the missed chance. In Italian, we also use another vehicle, actually. So instead of saying boat, we say treno, which means train. So from these trees, if we just look at the structure, we will, of course, extract a lot of meaningful correspondences if we look at corresponding parts of these trees, but also something which is not exactly correct. Of course, from trees, we can extract word alignments. So for instance, here we have the same structure in this subtree. And so we can extract the noun boat paired with treno, which is, as we said, not necessarily correct unless we restrict ourselves to this specific context. But we can also extract phrase alignment. So in this case, I'm showing what is an example of a verb phrase that we could extract. Miss the boat corresponds to perso il treno, or actually ha perso il treno. Right, so what's the relationship between statistical and syntax-based approaches? So we said that statistical approaches require large amounts of data, and syntax-based approaches might solve this problem because they can work consistently well, even on individual sentence pairs. We don't need a large amount of data. On the other hand, statistical approaches work with raw data, while if we want to perform 3-to-3 alignment, we need trees, of course. So the data needs to be analyzed. Third point is that in statistical, well, the output of statistical tools are correspondences between strings, while syntax-based techniques can return grammatical objects. And finally, with syntax-based approaches, we do not have to decide at what level of abstraction we work and have that fixed. So I said that this is an application of GFUD, but why? Why not just use GF? Well, the important point here was analysis. This is a crucial part of performing 3-to-3 alignment. And the problem is that the current GF parsers are not sufficiently robust. So because dependency trees are an easier target for parsers, if we, instead of performing 3-to-3 alignment on parse trees, we do that on dependency trees, then we can make use of more robust parsers, often neural parsers like UDPipe, which Aarne mentioned already earlier today. So this is the basic idea behind our software. So we start with some parallel text, we parse it, and this is something that we do with UDPipe in our case, but we could use any UD parser. So the result is UD trees, and we search, and this is what the new module, the concept alignment module does, for aligned UD subtrees. So we extract some correspondences from the sentence trees. And finally, we take these subtrees that are aligned, we convert them to GF3 alignments, and then those become grammar rules, the rules of a GF translation lexicon. Before we move on and take a look at how we can extract concept from a bilingual corpus, let's have a quick recap about UD trees for those who are new to this formalism or for those who are joining just now. So here you can see a UD tree in all the forms we can represent it. So first we have its graphical representation, then its standard representation, textual representation, Connelly, and this third version is a rows tree representation of the same tree. And this is actually what we use internally to the program. So first and most important, you will notice these links labeled with dependency labels. They connect dependents to their heads, so words to the word they refer to. So for instance, here, she is the nominal subject of the verb missed, which is the root of the sentence. It's important to always remember that all dependency trees have, of course, a root node. And so that's why we need the input to be sentence aligned, because by definition, two sentences are always alignable in terms of dependency label, because they are both, their head is marked in both cases with the label root. Then we have post tags, and Arne already said something about that. So each token is annotated with its post tag, which is here in the graphical representation and in the third column here. Here we also have lemmas. Well, I'm not showing them in the graphical representation. And then here I'm leaving a few fields of the Connelly file blank because they're not relevant for this discussion, but there's also lots of other information. So for instance, we have the morphological analysis of each token, which is actually useful later, but not central in this context. So how do we take a bilingual tree bank and extract concepts from it? Let's get back to our working example. She missed the boat, ha perso il treno. So the basic way to extract correspondences is very similar to what I showed for GF parse trees. So in this case, actually, we still look at subtrees in matching context. So basically, we explore the trees recursively. We start from the full tree, and then we look at its subtrees. So for instance, we can look at this subtree here, miss the boat, and this subtree here, perso il treno. And we compare dependency labels to see if there is an actual correspondence. And in this way, we can extract, well, in this case, 4 alignments. She missed the boat, ha perso il treno, missed the boat. So here we're already looking at subtrees, perso il treno, then the boat, il treno, which again is not entirely correct. And then the determiner here, the il. Of course, we are missing something. For instance, where is the alignment boat, treno? It's also important to align the heads of matching UD subtrees. So from the alignment, the boat, il treno, we also get boat, treno, which is again wrong. And from miss the boat, perso il treno, we get missed, ha perso. And here you might wonder why ha perso, also the auxiliary and not just the root verb, because the program is designed to extract the auxiliary to when there is one. And an alternative, or something that we can use in conjunction with comparing dependency label, is using part of speech tags. So in particular, we usually do that again by looking at corresponding, subtrees that are in matching context, so that are attached to the same head. And then we compare the multisets of the part of speech tags of its tokens. And we generally want to do that ignoring all or at least most function words. So in this case, if we are looking at this subtree and this subtree, we will ignore the determiner because it might well be, for instance, in Swedish, that the article disappears because it becomes a suffix of train. So these function words behave very differently across languages, and we want to ignore them. In this case, if we use this method, we get the same exact results as with dependency labels, but there are cases in which this can be used to increase recall when labels do not coincide exactly because there is a small syntactic difference. Or we can require that there is both a match in dependency label and a match in part of speech tags. And in this case, of course, we increase precision and we lose some recall. Then we can encode rules to handle some specific phenomena. One of them, which is implemented in the software that you can download and try, is rules for some translation divergences. For divergences, what I mean is systematic cross-linguistic distinctions. So for instance, one type of divergence is called categorial divergence. And here you see in English, we have the adverb distractedly, which becomes an adjective, distraherad in Swedish. In the second example, you see an adjective becoming a noun. Then we have conflational divergences. So here we see that there is this compound in Swedish, spelutveckling, which in English corresponds to two words, game development. Well, in this case, maybe we can say it's a compound written as two separate words. And then structural divergences. So here you notice the absence of a preposition, which is used in Italian. Head swapping divergences happen when in this case, for instance, we have the verb brukar, which means to usually do something. And so here the verb expresses one meaning together with the verb go. And here we have the verb which expresses both meanings. And last, we have thematic divergences. So here, this happens when the logical and grammatical subjects of sentences do not coincide, and they are expressed differently in different languages. Of course, nothing prevents us to encode rules that are more like specific to a language pair we're working with. We can easily add them. Or we could also encode rules for divergences, distinctions that are specific to the corpus we're working with. So maybe we have a corpus which follows some specific style, which has some specific style, and we notice that there are some divergences which are systematic, but just inside that corpus. We can encode those and use this. And then we can start with a non-empty set of alignments. So for instance, one thing that we can do is to first, let's say we have plenty of data. So we can first extract some alignments with a statistical tool, and then run concept alignment, maybe to extract multi-words or to increase the recall, or maybe we want to be more sure of the statistical results by seeing what both programs find. So this can be useful. Or we can reuse previously discovered alignments in an iterative fashion. So we apply concept alignment more and more times, maybe adding less and less strict criteria along the way. Another thing we can do, this is a recent addition, is that we can search for specific patterns, so specific types of alignments. And this we can do, this is the first way in which we use GFUD. Because GFUD has, well, part of GFUD is very much UD and not so much GF. So there are tools for pattern matching in UD trees and pattern replacement in UD trees. And this allows us to, for instance, just look for noun phrase alignments or just verb phrase alignments. And even with pattern replacement to generalize them. So for instance, let's say that we found an alignment between she missed the boat, ha perso il treno. From this, we can extract something that we call a predication pattern, which is some subject missed object, which in Italian becomes, well, there is no subject explicitly, ha perso some object. And a more interesting example, maybe, more classic example also, is this one. So in English, we have she told you that, which in Swedish becomes hon berättade det för dig. So here we have that some subject told some indirect object something, the object. And in Swedish, we have a completely different pattern. So there is again a subject, but then there is an object which says something för an oblique. So, but so far we have only talked about bilingual corpora, bilingual cases. Let's say that we are designing this machine translation system for 2 languages, let's say to translate from English to Italian and vice versa. But then at some point, suddenly we have to handle a 3rd language, let's say Swedish. How do we do that? What I described so far is what I refer to as concept extraction. And now we dive into concept propagation, which means we already know some concept, and a concept is defined as, in this case, a pair of UD trees. And in this example, let's say a pair of an English and an Italian dependency tree. And we want to find the expression that corresponds to that concept in a new language, let's say Swedish. And there are 2 cases in which this can be useful. First, there is the easy case, so I call it, which is when we have the same text translated in all languages. So this is something that we could solve even with the same approach described before by generalizing it to from pairs of sentences to tuples of sentences. So we could have some kind of n-lingual concept extraction, even though it's useful to do this in 2 separate steps, because maybe there are some correspondences that we are unable to find in English-Swedish, but that we can still automatically extract from for English-Italian, so that we have less manual work left in the end. Actually, the opposite is more likely, that we find something in English-Swedish, but not in English-Italian. And then there is a second case, which is a little bit more challenging, which is when we have work with some corpus in, let's say, English-Italian, and then we have another text in, hopefully in the same domain, which is in English-Swedish. So let's say that we have maybe Alice in Wonderland in Italian-English, and then we have Alice Through the Looking Glass in English-Swedish. They are in the same domain, so we expect many concepts to be shared, but they're not the same text. So this we can still do. It's a little bit less efficient, but we can still do it. And the approach is actually quite simple. I will not go into full detail, but the idea is that you consider the concept that you extract from the first 2 languages, and in particular, you look at the dependency tree for the shared languages, L2. Then you look for it among all the subtrees of the text in the new language. And if you find it, then you align the sentence it belongs to with its corresponding sentence in the 3rd language. In this way, you can propagate the concept in L1, L2 to L2, L3, and have a trilingual alignment, trilingual correspondence. And then there is one last step, which is generating the grammar rules of our lexicon. So, of course, this requires having alignment, which is what we worked on so far. Then you need dependency configurations for GFUD, but Aarne already said a lot about this, so I'm not going into detail about this. But then there's also 2 more requirements. First, we need a morphological dictionary of each of the languages involved. So in this case, 1 for English, 1 for Italian, 1 for Swedish. And fortunately, these 3 morphological dictionaries exist in the GFRDL. And then you need an extraction grammar, which is, well, let's first focus a little bit on the morphological dictionaries. Morphological dictionaries are unilingual dictionaries that contain all the morphological information one might need. So here is like a small portion of the English morphological dictionary. And then I said we need an extraction grammar, which is a grammar that defines the syntactic categories and functions that we use to build the lexical entries of our lexicon. So as an example, let's look at the prepositional noun phrases. So this is how we get from a preposition and a noun phrase to a prepositional phrase. And what you see here on the right is the dependency labels for GFUD. And if we have all these ingredients, let's say, then we are ready to generate our lexical rules. And here, as an example, I'm showing something which is a multi-word, just to show how it looks like. So usually they look like this. We have, here is a bilingual example, English-Swedish. So the first part of the identifier is the English, in this case, multi-word. And here we have it's a Swedish translation. It's a prepositional phrase. So remember what was in the extraction grammar. And for instance, in the English concrete, its linearization looks like this. How do we get to this? So first, we use GFUD, actually UD to GF, to convert the UD trees, three pairs or triples, to GF pairs or triples. And well, here I have to contradict Arne maybe. He said that UD to GF is nearly unusable. Well, in this case, it works very well, actually. And it works very well because usually we are interested in as small as possible alignments. So single words or small multi-words, such as this prepositional phrase. And that means that we can easily overcome the limitations of UD to GF by limiting the size of the trees we work with. That's the simple solution in this case. So, and then of course, then there's something more happening because trees are converted to grammar rules. And so this is a small addition that was performed to GFUD recently. So now we have sort of the full picture, I think. We start with strings in 2 or more languages, let's say in 3 languages, so that we make use of both extraction and propagation. We parse them, and this is something for which we rely on some existing technology, UDPipe. From this parsing step, we obtain dependency trees. So we obtain, in this case, 3 different tree banks of aligned sentences. Then we can perform extraction, whose output is pairs of dependency trees that are aligned. We can propagate them to the 3rd language. So we have trilingual alignments. And then we use this extended GFUD to convert the UD trees triples to first GF3 triples and then grammar rules. Of course, we can't expect the results of this to be perfect or to be comprehensive, not always at least, unless the texts are really, unless the translation is really literal and unless the languages we work with are really syntactically similar, we can't expect it. So we are developing some post-processing tools. So first, this is a very recent addition, very recent, like last week, I think. What we can do is to interactively select the alignments that are correct, or in any case, useful for our machine translation system. This is an evolution of former debug script. So what we can do is we see the alignments linearized as just plain text sentences, and we can mark them as correct, and usefully want to use them in the translation system. Correct, but we don't really care for the translation system. Maybe we extracted something that is correct only in a specific context. and so we don't want to use it, or completely wrong and to be thrown away. And then another thing that we found useful when the recall of this method is not sufficient is to look at the UD trees in the various languages simultaneously. So there is a small Connelly viewer that can help with that. You can just compare UD trees and add to the automatically generated lexicon. So in summary again, first we have this parsing step powered by UD5. Concept extraction is the process of extracting correspondences from a bilingual corpus. Concept propagation is what we use when we have to handle more than 2 languages. And then the last step is generating the lexical rules. And as an additional step, we can have some manual post-processing. Here you can find links to everything I mentioned so far, if you wish. And another way you can know more is by asking a question right now.
Thank you. Questions? Yes.
Hello, very nice talk. It's actually I don't have of course I will have general questions regarding the links to the slides, because the last slides will have a bunch of links, and that's probably they are very interesting. But one comment about that is that I have been working with the glosses of WordNet, finishing the work with the disambiguation of the glosses of WordNet, and also in the Portuguese WordNet. So I have the translations of the glosses to Portuguese. So I wonder how this process could be augmented with we have the disambiguated words against the WordNet itself, right? So we have the words of the glosses disambiguated in both versions, at least 2 versions, Portuguese and English WordNet. Because I'm raising this question because I raised this comment because I know about the project that was presented here, but I didn't have a chance to attend about the use of WordNet with a grammatical framework. So I wondered if your project or you can see any connection between the work that was done with WordNet and your work.
Yes, so we thought about using the WordNet actually from the beginning, I would say. And that was meant to be used to automatically, to automate part of the process of selecting the alignments. So I think this would be very useful. And well, then basically while I was working on my thesis project, there was no time to implement that, but that's definitely in my thoughts. Because of course, actually not the most demanding, but the most tedious part of the evaluation process is this manual selection. And if we could avoid that, of course, that would be a huge step further.
Okay. Thank you. Yeah, let's talk about this. Maybe you can collaborate somehow.
Yes.
Yeah, go ahead, Arne. Ask your question.
Yeah, no, I think I was wondering how you decide that the boat and Treno don't align, and I think the WordNet would actually give you a hint about that.
Yes, that's one case where actually knowing that they don't align is very easy. Yes. Then, of course, in that case, there is a correspondence. It's just that it's not useful in it's so useful in almost no context. So that's why we discard it. Yes, in that case, WordNet would do the job.
But otherwise, I think so that for many of these, let's say, normal one-word correspondences, so you get a lot from WordNet, but there are two things that you don't get from the WordNet. So one is many of the multi-word things, as you said, which we were also focusing on. And the other one is if you want to have something very kind of either domain specific or even, let's say, enterprise specific. So we were analyzing some data from a customer who wants to use certain words for certain things when they translate, and that's they can be very picky about such things. And then if you study their corpora, then you can find those just the right words that they want to be used.
Yes, in fact, I'm not saying that using the WordNet would replace, obviously, all the manual post-processing, but
no,
part of it, yeah.
But of course, so this is the focus is in some sense on things that the WordNet doesn't give us already. Yes.
Also, I would say that multi-words are easier to select manually, even when you don't know the languages. If you look at the UD trees and see that the analysis can't make sense, then you can discard them safely.
Yeah, so then what is done is by the tool is to convert these into GF rules.
Yes.
And there, I mean, of course you are right. So when I said that the UDGF doesn't scale up, I meant that if you have a large grammar and or long sentences, then it gets very slow. So that was what I meant, but it works quite well for these small and simple things, even if the volume is large in terms of the vocabulary.
Actually, yes, in this case, if you don't limit the size of the trees, you get actually a lot of not very meaningful alignments. So it's actually better to only work with the small ones.
Let's take Krasimir, and there's also questions in the chat, or maybe rather comments. Yes. I think Krasimir had his hand first.
So just 2 comments about the integration with WordNet. First, once you align words, you can try to look up in WordNet, and the fact that you have 2 translations would disambiguate, but you will still get ambiguities, of course. And then the example with train and what was it, boats. Sometimes you get also translations like this in WordNet, like for example, juice translates to soup in Swedish if you mean that juice is the energy that powers something.
Yes.
Very strange correspondences. There are also other examples. And this is one more interesting case. The other connection that I thought would be really nice is not with the WordNet, but with the grammarian, because there I show that you can actually do non-compositional translation by using the block for idioms. But then actually even better is that you write something in English, you parse it, and you see, okay, in Swedish it's okay, in French it's maybe okay, but in Italian it's not okay. And then you just type in the Italian phrase, you parse it again, yes. And then you do this phrase alignment, and then the idiom block should be automatically extracted. This would be really nice to have one day in the future.
Yes, that's definitely something to look into. I agree.
Yeah, no question, just comments.
Yeah. Next questions. Alexandra and Rhett. So.
Yeah, I'm not sure if I follow this last comment, but one related thing that I have is during your presentation, I kind of start to map the Italian examples to Portuguese, and some of them I come to my mind that could be paraphrased, right? And the paraphrase could be much more similar than the source language, right? And I don't know if you could, for example, use this approach to, if you have imagine that you have some threshold in the distance between trees, and then you can try to parse the target language and then produce some kind of a paraphrase and try to see if the tree of the paraphrase could be more similar than the source language.
Yeah, that's very often the case. So actually, in some concrete cases, one thing that you can do when you don't have these example sentences is to, or at least maybe you don't have them in all the languages that you have to handle, then you can ask for a literal translation. And in that case, of course, the results are a lot better. Yeah. Yes, that's definitely, I agree with you.
Did Loretta Krasimir have a question? I saw your hands were raised.
I think I did have a question, but then maybe I might have just missed it. So I was just a bit confused about so the post-processing, how much of a manual process that is until you get to your GF lexicon that you can use in your application grammar.
Right, that's
but
difficult to know.
Okay.
It really depends on many things, actually. One factor is how similar are the languages you're working with syntactically, similar to each other. That's the first thing. Then another important thing is how good is the UD model that you're using. Of course, you can train your own if you have data, annotated data, but in general, so far I relied on pre-trained models and they work very well for English, for instance, surprisingly well for Swedish too, not so well for Italian, for example. And then the third point is just how does the text look like? So for instance, if we apply this to the example that I showed in the beginning, which was a parallel version of Alice in Wonderland, then in that case, I expect the results to be quite bad, because then it's not so much a matter of how similar the two languages are or how good the models. The point is that when we work with literary translation, often specific choices are made by the translator that make it so that the sentences don't look similar to each other. But let's say we apply this to an instruction manual. In that case, generally the translations are quite literal, or to some technical text in general. So these are the three factors. And then there's, as I mentioned, there's two types of post-processing. So like one thing is selection, which is boring, but it's fast, and it can be faster with the WordNet. But then there is also the part which is about adding all that was missed by that system. And this can also be made faster if there's enough data with statistical alignment, as I mentioned. So you can use them in conjunction with each other. So it really depends on the context. That's the answer.
Any more questions, comments to any of the two talks?
One more quick question. Can we find this in the GFUD repository on GitHub? How much of the code is there already?
All the code is on GitHub, but it's not in the GFUD repository. So in the slides, you will find a link to the concept alignment repository. And you do need GFUD to use it.
Okay, thank you, thank you.
That's it.
If there's no more questions or comments, let's go on a lunch, dinner, breakfast break, and we resume at 7 p.m. for Michal's talk.
All right, see you later. Thank you all.
See you later.